Now let's talk about buoyancy. According to Archimedes, who discovered, he's a Greek scientist, Greek philosopher rather, philosophers were scientists back then, who discovered buoyancy. According to him, every object submerged, whether partially or completely within a fluid, exerts from the part of the fluid a vertical upward push, a vertical force, equivalent to the weight of the fluid that has been displaced, to the fluid that moved away. In other words, the volume of fluid that moved from the way when it was, submerged, when the object was submerged. So the volume of that fluid that moved from the way as it got replaced by the object drowning partially or completely, if you get the weight of that volume, which is W is equal to mg, it will be equivalent to the upward force exerted by the fluid against the object. This is the very force that allows wood, bows, and even ships to float above water. Let's simplify it with an example. Consider a box of 2 meter length, 1 meter width, and 1 meter height, or depth if you will, plunged into water. Only half of its height is submerged, which is 0.5 meters. So what is the buoyancy force being exerted against this box? Let's start by calculating the volume of the water that has been displaced, which is the volume of the box underneath the water. So the volume is width times length times height, WLH, correct? Is equal to width is 1 meter times length, which is 2 meters, times 1/2 meter, 0.5, is equal to 1 meter cubed. Alright, so you have the mass of the volume after we had found the volume is equal to rho times V. Rho being the volumetric mass or density, in other words, of water. So M is equal 1000 times V, which is the volume. So actually, we don't need to immediately evaluate that. We can place this value of M, or the mass, in the weight of water, in the weight formula, which is also the upward pushing force or buoyancy. So weight is equal mg, then weight is equal to rho vg, because m is equal to rho v. So then it is equal to the 1000 times 1 meter cube times g, which is 9.81, actually not 9.875, but anyway, it is equal to 9875 newton if we assume that the gravitational acceleration is 9.875. That same weight of water is pushing the box upward. That would become also not only the water, the weight of water that has been displaced, but it is the same force acting upward against the box. That's the force of buoyancy that has been created due to the submerging of the object. Okay, so the same weight of the water that has been displaced is actually equivalent to the buoyancy force pushing the water, the box upwards, forcing the box to float on this water. All right, that's the very definition of buoyancy. According to Newton's first law, now here another perspective, a deeper perspective. According to Newton's first law of static and dynamic equilibrium, when a body is motionless or when it is moving with a steady velocity, acceleration is equal to 0. This is a static and dynamic equilibrium respectively. Then the sum of all forces acting on it is 0, correct? Sigma F is equal to 0. In Newton's second law of motion, the sum of all forces, vectorial sum, acting on a solid or a particle in motion is equal to the mass of the solid, mass of the center of gravity if you will, times the acceleration, A. Acceleration is the rate of change of speed during 1 second of time. So going back to the box floating in the water, by applying Newton's first law and considering the mass of air is negligible, we get sigma F is equal to 0, Fb, which is the buoyancy force, minus weight, Why? Because they have two different directions. Okay, so these are positive and minus vector. Okay, positive and negative vectors, they are opposite against each other. You need to place their vectorial value, their vectorial sign. So FB minus W is equal to 0, then FB is equal W. If we take that the downward direction is the -1 within this scale. So since the box is not droning, it means that the pushback buoyancy force is equal to its weight according to Newton's first law. Hence, we can find its mass, yes, okay, with this value of buoyancy. So in case weight was greater than the buoyancy, the box drowns until it hits the water bottom. But here in this case, since it is floating, then the buoyancy force is equal to the weight of the box, and through the weight, by the formula W is equal to mg, you can also find the mass of the box in kilograms.